Okay, now let's talk, and I realize, yes, I made a mistake. I didn't put the angles on 2 and 3. Chill out.
How do we actually do that?
Okay, so let's talk about the problem. So here's this block of wood sitting on a 20-degree angle. Okay, here's the block, boom, up, coming down like this. So for now, don't even worry about this. Okay, don't even worry about this for now. We'll deal with this later. So the whole key is that you're going to pull this thing up at a constant velocity. Okay. Now, if nothing else, here and you're going, God, I don't know what forces to do. Okay. What you might consider doing is just setting up a chart, because especially on inclined plane problems, there's basically going to be 3 potential things that could happen. Your net force, your force parallel, your force friction, right? And maybe a force applied, okay? We'll get it, and then if there's also potentially like a magnet, that would kind of be like that frictional force. We'll get into that when we get to that part. So if nothing else, set up a chart and go, okay, do I have to worry about all 3 of these? Do I only have to worry about part of them? Which ones do I have to worry about? Is my net force going to be a 0 value? Is it going to be a non-zero value? What's going to happen? So right away, what's the value of my net force going to be? 0. So I know when I add up all of these, I have to get a value of 0 because it's at a constant velocity. Now, of these 3 on an inclined plane, what is the only one that will always be there? Parallel. The parallel force is the only one that will always be there. It might be frictionless, there might not be an applied force, but you will always, always, always have a force parallel. There's no way that can go to 0. Unless you're on a flat surface, then you don't have to worry about it. Okay? But on an inclined plane, there's always going to be this force parallel. Always, 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 always. Now, how do you get your force parallel? FG sine theta. Okay? Or mg sine theta. Now, again, you have to make a decision. Do you want to make that negative? Do you want to make it positive? I don't care. Okay? But you're going to get this value. For the sake of argument, let's say that that's 2. Okay? I don't know what it is. Let's just say it's 2. Okay? Whatever it is. Okay? It's a value.
Take the 0.8 then times
Hold on.
gravity.
No. Hold on. Now, let's talk about the frictional force. To do this, you've got to use mu equals force friction over force normal. Now, what are you going to do wrong on your normal force? What will you forget to multiply by?
Cosine.
Cosine of the angle, because this is force normal. It's Fg cosine theta. So you've got to take mu times mg cosine theta. Now here's the decision that you have to make. This block is being pulled up the inclined plane. Okay? Being pulled up the inclined plane. So which direction is my friction going to act?
Down.
Down. So my force parallel is acting down, and my force friction is acting down. So both of those values have to have the same sign. So let's say that I calculate my force friction, I do all that, and I get 1. Okay? Now, if you want to make these both negative, fine, make them both negative. If you want to make them both positive, make them both positive. I don't care. Okay? Just pick a system. So, if, let's say these two, I'm going to make these two both be positive. That means my applied force has to be, in this case it would have a value of -3. So, if I take a -3 plus 1 plus 2, boom, I get 0. I have a net force at 0, I have motion, but I have motion at a constant velocity. So here's the trick. There's 2 ways, there's actually an infinite number of ways that I can produce a 3 Newton force. I could take a little fan and bolt it on the top of it, and have the fan turned on, and that fan could produce 3 Newtons of force. That would be an option. Maybe I have a trained physics penguin that pushes with exactly 3 newtons of force, which would be cool, don't get me wrong. They're hard to come by. Okay, so let's negate the trained physics penguin. Or we can let gravity pull on this weight out here. Okay? So what I want to know is what mass do I put out here to generate 3 newtons of force? So here's the deal. Let's just take a guess. Let's say, well, we put a 1 kilogram mass out there. I like 1 kilogram masses. They're kind of cool, got a nice shape, kind of certain heft to them. Hey, hands in, 1 kilogram. Okay, but here's the deal. If I put a 1 kilogram mass up here, how much force is that going to generate? 9.8 newtons. 9.8 newtons is greater than 3, so if I put a 1 kilogram mass out there, this thing's going to accelerate, because then my applied force is going to be bigger than these other 2 forces. So 1 kilogram is too big. Okay? What if I put a 0.1 kilogram mass? Okay, 1's too big. Let's try 0.1.
No.
Why?
Then you get 0.98.
Yeah, so 0.98 isn't enough. So you can try a whole bunch of guess and check things. I don't recommend it, okay? I don't recommend it. But here's a simpler thing. I got 3 newtons. So 3 newtons, right, is going to equal some mass times 9.8 meters per second squared. How can I find the mass? Take whatever that applied force is and divide by your gravitational acceleration. Okay? That's the simplest way to do it. Good with that? Fantastic. Now, let's talk about the next one down on number 3. So if you look on number 3, let me see the sheet. So if you look on number 3, what mass be suspended from the strength of this block will slide down the inclined plane. Now here's the deal. Because it's sliding down, does my force parallel, does that change anything about my force parallel?
No.
No, it's the exact same, right? Still the exact same. It's still the same numeric value, and it's still pointing down the hill. When the block slides down the hill, is that going to change the value of my frictional force?
No.
The value is still going to be the exact same. But what is going to change about it? The sign. Now, my frictional force is going to be acting up the hill. Okay? So now, draw another chart like this if you're not sure what to do. List all of your forces. Okay? If you get in a problem like this on the test, and on the review, this is how I've worked a lot of these problems. I've said, okay, here's a chart. Let me list my possible values. So I still want my net force to be 0. I still have my force parallel. Then I still want everything to add up to equal to 0. So then I switch the sign to my force friction. I use that to determine my force applied. Now, here's the deal. Let's think about this. Is your answer to number 3 going to be a bigger or smaller mass than your answer to number 2? Smaller, because in effect, friction is helping you out. Because you're trying to let this thing slide down at a constant velocity, so friction's actually helping you provide some of that force. On the way up, friction's working against you, because now it's working in that opposite direction that you're trying to pull. Okay? So even if you get a problem like that, just stop, think through it. It's like, okay, rightio, what's going to happen here? All right, yeah, okay. So, everybody good with that? There's one diagram to do with that lab, and it should look something like this. This is that one. So you're actually going to draw a 30-degree angle. Okay, this isn't just some random drawing. This is an actual 30-degree angle. You're going to put your box, okay, and then you can have like, oh, here's FG, set to some scale. Your force parallel, your force friction, your force applied, your force normal. Okay? When this gets done, you should have 5 vectors. Okay? Count them 5. And here's the first thing that I'm going to look at when I look at this portion of the lab. you've got a fat going up, and then you've got a force parallel and a force friction going down. Here's the first thing I'm going to check. I'm going to look at your force friction and your force parallel, and those two values added together should equal the applied force that it took to pull it up. Okay? So if you want to make sure that you have that part right, find your force parallel, find your force friction, add those two together, and those should equal whatever the measured applied force is. If it does, you're set. If it doesn't, that's bad. Okay? Man. Help me, Rhonda. Okay.
Rhonda?
You ever heard that song? Help me, Rhonda.
Do you want me to turn it
It's
off?
Beach Boys, I think. Okay. You do it? Yeah. Okay. No, are they both working?
Yeah.
That's just weird.
Yeah.
Okay.
There's like 3 of you.
Pick one.
Mr. Bergkamp?
Yes?
This revised diagram on the back of the blue sheet,
I
since
didn't
there's a lot of
do it.
space.
Yeah, that's fine.
Okay.
That's fine.
Oh, you didn't put yours to scale?
Okay.
Everything
Now,
okay.
let's talk about the magnetic field lamp. Okay?
Alright.
Let's talk about that. And I promise you, on the test tomorrow, there's going to be a question about this magnetic field lamp. Okay? So make sure that you understand it. I promise you, I'm going to ask you a question about this on the test. So let's talk about it. So here was the setup. Okay, here's your inclined plane. It's not near this steep, but there's the work. So in an ideal world, here's what I wanted to have happen. When I built these, I set that length of that aluminum plating to be 40 centimeters. So that's why I wanted you to have a displacement of 40 centimeters to measure that acceleration. So let's look at what's happening before you put the magnet in there, okay? Without the magnet. What's the only force available to accelerate the system? There's no magnet. What's the only force available to accelerate the system? What component of gravity? Force parallel. Okay? So the only game in town to make this thing accelerate down the hill is your force parallel. That's it. There's nothing else. Now, what we initially assume is that there's no friction. Okay? Realistically, there might be some. Okay? But we're going to assume that there's no friction. So there's two ways you can get your theoretical acceleration. One option is that you take your force parallel divided by the mass, get the acceleration that way. That's cool. The other thing that you could do is you could use A equals G sine theta. Okay? You know the angle, take the sine of the angle, multiply that by 9.8 meters per second squared, get the acceleration that way. You should get the same theoretical acceleration no matter how you do it. By either taking your force parallel and dividing it by the mass, or using A equals G sine theta. It is the exact same math, you just change the sequence of how you do stuff. Okay? It should be a pretty small number. Okay? It should be a pretty small number for your theoretical acceleration. Because you only have you'll probably have about a 2-degree angle. So it's not a very big acceleration. Okay. Got that. Now, then you're going to calculate an actual experimental value using x equals 1/2 AT squared plus V naught time. So you're going to use this 1/2 AT squared plus V naught time. Being the brilliant physics students that you are, you said, oh, this is clever. I'm going to start it at rest. I'm going to know the time. I'm going to know the distance. I can get my acceleration that way. Now, probably, notoriously what happens, this acceleration here tends to be a little bit less than your theoretical acceleration. That's normally how it plays out, okay? Normally. It might be greater, but normally it's less, because there's normally a little bit of friction in the system. Okay, so you've got this. All right, son, okay, here's my actual acceleration. So then, the next part is you put this magnet in here. Now, this only works to a noticeable effect with really strong magnets. So the short version of why this works is that if you look at this magnet, okay, magnets have what we call magnetic field lines that come out, and look at that, hold on, I can get the thing.
Because you just do, you pick whether it's down.
Or did you just read this? Oh,
Yeah.
you put
You pick
not
like,
just kidding.
like if 4 person going down, 6 person going, you either make them negative or you just you just pick.
Okay.
Pick
Or I can just do it on the sheet.
In the space below.
Or I can just do it on
So there's
the
a couple of different ways you can show like the existence of magnetic field lines. And what I have in here is just like, kind of like a granulated item. And so if I put that on there, you can see that those things tend to come to a point, okay, which indicates that there's that those magnetic field, even though you can't see it, it actually exists within lines. And it's a very good example of an inverse square law, because if I'm far away, the magnetic field isn't as strong. If I get it closer, the effects of that magnetic field become much more pronounced. Now, if I turn it on the side, like this, you'll notice that you get a different shape because the magnetic field lines are coming out of this side. This is why when I set this up, I had to have the magnetic field lines coming out on the side so that when it ran down that aluminum, the magnetic field was interacting with the aluminum. If I did it like this, and the magnetic fields were going this way, and the plate was going like this, you wouldn't get the effect. So the other thing that you can do to show this is using this ferrofluid, which is just hours of entertainment fun. So this is like the same material, but it's suspended in a like mineral oil. And so that's the other way you could see that those things come to a very, very distinct spike because of the fact that you've had that presence of the magnetic fields. Yeah, hours of entertainment fun right there. Okay, just saying. No, no, huh? Yeah. I mean,
Three.
and then you can do.
Oh, that was creepy for a second. I thought you'd like jam something through your hand.
No, no,
I
no.
really
All it is just got the magnet on the back, okay? It's nothing creepy, all right? It's just a very, very strong magnetic field. Okay. So, it's not Halloween, believe me, I hate Halloween and all things creepy about Halloween. Okay. Has to
come to your house
has to do with
scary.
a witch at a grocery store, it's a long story. Okay. Oh, you really don't. So here's a short version of what happens. So when this aluminum, which is not at all attracted to the magnet itself, what happens is that, but it is a metallic metal, it's aluminum. So basically what happens is that the aluminum senses a change in this magnetic field because it starts to move through. So basically what happens is that the aluminum itself then creates a current that opposes this magnetic field. Because nature basically says, wow, there's a changing magnetic field. I don't like this. I am going to do something that opposes it. So within the aluminum itself, on both sides, it induces its own current to oppose the change in the magnetic field. And the greater the rate of the change is, the greater the force. So that's one of the things that was hard to pick up. But so basically, when that thing starts in going really, really fast, it actually has more of a braking effect as it's going faster than it is when it's going slower. So that's when you can get into calculus and take the derivative as a function of speed, and that affects your braking force. Okay, so here's the deal with this magnet. So which direction did the force from the magnet act on the plates. This is the whole crux of this lab. In the opposite direction. So it always creates a force acting in the opposite direction of motion. So in some ways, this is like magnetic friction. Okay? It's like magnetic friction, but it's not actually touching it, because that gets really cool, because then you start thinking like, wow, I'm creating a force and there's nothing physically touching, but yet this is slowing down, but yet there's nothing there to actually do it. So it isn't like it's scraping the sides of it. And so on an atomic level, what you would see in the aluminum itself is that it's creating its own little current, which is creating its own magnetic field, and that's what opposes this. And so that's the cool part of it, because if you think about it, it's a true story. If you think about it too much on how it works, you'll do drugs. So let's just not think about it too much. Okay, so here's the point. No, it's true. If you really get into what happens on an atomic level, it is so weird. No, just don't think about it.
What comes left?
Okay, so here's the point. The force from the magnet always opposes the motion. So the force, call it force magnet, okay, is always in the opposite direction of motion. Okay? Always in the opposite direction of motion. Now, on the very front page of this lab, up here at the top, I've got down the incline is negative and up the incline is positive. Keep this in mind when you're calculating your values. Everything going down is negative. Everything going up is positive. Okay? So like even at the beginning, when I say, hey, you know, and Hunter, to his credit, has this right, I said, what's the theoretical acceleration of the car? He's got a negative value because that's going to be going down the hill. Okay? So what you're going to look at is this. It's the same idea if you want to set up a chart and go, okay, I've got a net force. I've got a potential applied force. I've got a potential force parallel. In this case, I've got a potential force from the magnet. Now, let's look at this. The first time through without the magnet, was there any applied force? No, didn't have to worry about it. That's zero. Was there a force parallel?
Yes.
Yes. Okay, that's going to be same negative number. Was there any force from the magnet? No. So the only net force that you had initially was your force parallel. That's it. There's no other game in town. That was it. Okay? We assume that was the only force available to accelerate this system. Now, this is no magnet. Now, with the magnet, okay, do I still have a net force that is not zero? Yes, because otherwise, if I let go of it, it wouldn't accelerate. Okay? So, is my net force still going to be a negative number? Yes, because it's still accelerating down the hill. So this is going to be a negative number. Now, remember, net force always equals two things. Remember this, remember this, remember this, remember this for the test. Net force equals two things. It equals the sum of all of the forces, but it also equals what? Mass times acceleration. Now, what do you use for the mass?
The total mass.
The total mass of the system, no matter where it is, that's going to be the entire mass of the system, which we'll talk about later in just a second on a demo that I've got back there. Okay. So, is there any applied force?
No.
No. There's no penguins, there's no fans, nothing. This is still zero. With the magnet, did that change my did that change my force parallel? When I put the magnet in there, did that change my force parallel? No, because it's still the same weight of the cart, it's still the same angle. This is still the exact same number. Okay? Now do I have a magnetic force? Yes, and what's the sign of that magnetic force going to be? That's going to be some positive number because that's pointing up the ramp. So, what you're going to do is you're going to find this number because you're going to know the mass and you're going to know the acceleration of the cart. So you're going to be able to determine this number. You're going to know the force parallel because it's the exact same force parallel that you had before. So what's the only thing you don't know?
The magnetic.
The magnetic force. Okay? So there's two things that you realize about your magnetic force. It should be a positive number, and is it going to be bigger or smaller than your net force? Well, let's say that's -1.
Well, if it gets it to stop, it should be bigger.
Yeah, but we're not stopping it.
All right, that's small.
Yeah, there you go. Okay.
Simple question.
All right. Are we cool with this? Everybody good? Now, what would happen if there was actually friction?
Do we have to find that?
Yeah, because you'd also have, if there was actually friction in it,
Thing?
you'd have this action going. Okay? Now, how could I make an applied force that wasn't zero? What could I physically do to create an applied force that wasn't zero? I could push it. Okay? What's another thing that I could do?
Penguin.
Tough. Yeah, I could. I could use a penguin. I think that falls under the push category. No, let's go to the back. Just keep that. Let's take the big camera
Okay.
and let's just keep that rolling. And don't stop it. I think that's where we might run into trouble.
Shut this one off?
Yeah, shut
You don't
that
want
one off. I know that one will start back up. Keep that one going.
Okay. Just have to do some fancy cutting.
Okay.
Why would I do that?
Okay. So here's what we've got set up. So I've got a 50-gram mass on the end of the string, right? That's running parallel with the ramp. I've got the magnet set up in here, and I've got a little stop right there. So right now, everything's in equilibrium, we're not moving, all this good stuff. So I'm going to pull this out. Let's little train that could. Now, watch what happens. Any number of cool things happen. But watch what happens when I let go of it. Okay? Now, as soon as I let go of it, what does it begin to do?
Accelerate.
Accelerate. So, right now, here's what I want to look at. When I let go of it, let's not worry about the magnet for now. When I let go of it, which force is bigger? My applied force from the weight or my force parallel?
Applied force.
Yeah, because if my force parallel was bigger, what would happen?
You go that way.
Yeah, I'd let go of it, it would roll downhill. Okay? So, I know this force has to be bigger. Now, as soon as I let go of it, it begins to accelerate, which right away means my net force is not zero. So if you want to define this as being positive, okay, my applied force in a positive direction has to be bigger than my force parallel. Now, because it's not moving, I have no magnetic force. This only works when you have a changing magnetic field. Now, as soon as I let go of it, then I start to create that opposing force. Now, at this point, if you look at what's happening, do you think it's still accelerating even right now?
Looks like a constant. No.
Pretty constant. Okay? Now, as soon as it clears the magnet, what does it begin to do? Then it really begins to accelerate. So when this thing, put that back up. Okay. So when this is sitting here like this, okay, and it's rolling, right? We kind of hit a point of almost like a constant velocity. So when this thing hits, let's just play the what if game. Let's just assume that it's at a constant velocity when this thing is moving. So what are the three forces?
Parallel, magnetic, and applied.
Okay. So you don't get to answer any more questions.
Oh, you hurt my feelings.
It's okay, get over it. So when I let go of this thing and it's moving at a constant velocity, Sam, we're at a constant velocity. So all the forces have to add up to
0.
So what are the two forces acting down the hill?
Force parallel and magnetic force.
Yeah, okay, we'll call it magnetic force. So I've got these two forces acting down, which is doing nothing but balancing out the force from the weight pulling this way. So what happens is that when I let go of it, it initially speeds up. But what happens with that, then this is the cool thing about this magnetic force, is that the faster it goes, the stronger the magnetic force becomes. So basically when I let go of it, and it starts to speed up, that magnetic force is getting stronger. But then it can't accelerate any faster because of the fact that it's like hit its limit. So everything is constant. Now, as soon as it clears it, then it begins to accelerate again. Because what do I lose as soon as I clear the magnet? Of the magnet. I still have an applied force, right? I still have parallel acting down, but now I've lost this. Now, let's say, here's a trick question. So let's say I wanted to calculate that acceleration right at the beginning. I want to get the acceleration at this point from here to that point where it becomes a constant velocity. What are some things I could measure?
2d divided by t squared.
Keep going. What'd you say?
2d divided by t squared.
Okay, so I can measure the distance, and I can measure the time. Okay? That would give me my acceleration. Cool. Now, I could use that to calculate my,
Acceleration.
I got that. But once I get the acceleration, I can use that to calculate my,
Mass.
no, let's assume that I know the mass.
Force.
Which force?
Net.
Okay. Now, but here's the question. Speaking of mass, if I wanted to calculate the net force, which mass would I use? This up here, or the 50 grams, or the entire system? The entire system. So when you have a setup like this, which you're very likely to have on the test tomorrow, okay? When you have a setup like this, don't. When you have a system like this, and you're trying to calculate that acceleration, always use the total mass of the system. Remember that, remember that, remember that tomorrow on the test, okay? It's going to take that mass out here plus this entire thing. Now don't include the magnet because that's not part of the system, okay? So if you want to calculate that acceleration, there's a whole bunch of things you could do. But any mass that you use is always the combined mass of the system. Now, what would happen, pull that out. So what if I did this on a flat surface? What should happen to my acceleration? Ellie, what should happen to my acceleration?
It should speed up because you don't have force parallel anymore.
Beautiful. So now when I let go of it, I get a bigger acceleration because now I've lost that force opposing created by my parallel force.
Wait, was it inclining down or up?
Huh?
Was that side inclining down or was that side up?
This side?
Yeah.
It was up.
Oh yeah, alright. Sounds good.
Okay, we're good?
Yeah.
Okay. So,
I couldn't see your covering.
But I mean, we moved
yeah.
There was no.
Just no. Okay. So now I get a much bigger acceleration because of the fact that I've lost that force parallel. Now, by making it a flat surface, did I change my applied force? No, that stayed the same. But I made smaller my opposing force. That ended up a greater net force and a greater acceleration. Okay, beautiful. All right, back we go. How do we flip that?
Trust me.
Do you want the other one on?
Yeah, turn that one back. All right, so let's talk about what I promise will be on the test tomorrow. I promise you there's going to be a rocket problem. I promise you there's going to be a rocket problem. Promise you, promise you, promise you. And I'm going to tell you, no, you are going to completely lose all focus. No. Okay, when I get done, you can, okay. So, here's what this is exactly how the problem's going to play out. I'm going to say, okay, the force from the engines is 40 newtons, okay, whatever it is, all right? And then the mass of the rocket is 2 kilograms, okay? And I'm going to ask you, what's the acceleration of the rocket? What I'm going to do. So what are you going to do wrong?
Take 4 times mass.
You're probably going to assume that the...
You're going to take 40 newtons and you're going to divide it by 2 kilograms, and you're going to get 20 meters per second squared, and score! That was easy. Okay, moving on to the next problem. Okay?
But it's gravity also.
Oh, there's gravity. So again, if you're on the test, make a simple chart. Go, okay, net, fat, fa. So the 40 newtons is my applied force. So what could potentially be my opposing force?
Gravity.
Gravity. And how are you going to get that value? Multiply 2 kilograms by 9.8. Now, if you're defining up as being positive, then you do need to make this a negative value. Okay? So, that becomes, should be 19.6. Negative 19.6 plus 40 should get you 20.4, which should get you an acceleration of 12.2 meters per second squared.
Wow, that's easy. Wow. 3 points right there, boys. Write it down.
All right. Now, what's the only time you don't have to worry about this opposing force?
Space.
And I will,
Deep space.
And I will, if I do not want you to worry about gravity, I will explicitly tell you.
I need this rubber band.
You got it?
Yeah.
Okay. I will explicitly tell you, you don't have to worry about the effects of gravity. Unless I tell you that, you better worry about gravity. And there will be a problem, and it will explicitly tell you the effects of gravity can safely be ignored. Other than that, you worry about gravity.
Safely, or what if it's like dangerous?
Reasonably.
All right.
Okay. Why'd you divide by 2?
Because the mass was 2 kilograms. I just divided by the mass.
So we could do that, or just take 9.8, or just force equals mass times acceleration. So we still do that?
Yeah, that's what we did. We
Okay.
took that net force of 20 newtons, divided it by the mass of 2 kilograms, and got this acceleration.
Oh, okay. Okay, yeah.
Yeah, yeah? Okay.
Hey, can I get the rubber band?
No. Okay. Now, I promise you,
You're making a lot of promises.
I am.
Hold on, I have a quick question.
You're going to have a problem like this, where you have a mass suspended from a table. I promise you there's going to be this. So again, set this up. If you're not sure, go, okay, net, FAP, FOP. So what's the only force available to accelerate that system?
The mass suspended.
Multiplied by
Gravity's acceleration.
gravity's acceleration. So whatever this is your applied force. So take that times g. That's it. Now, if I tell you it's frictionless, what's your opposing force?
Zero.
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 Nothing.
So that means your applied force is the same as your net force. Now, how are you going to get the acceleration?
Force divided
Force
by
net equals mass, find the mass of it.
Which mass do you use?
total.
Use the entire mass of the system.
Including the stream.
Now,
I'm getting it 100%.
Dude, don't ever say that.
yeah, you did that on last test. How'd that, yeah.
I said 95. That's
No,
what I
you
got.
didn't.
Yeah, I did. I said this is about 95, and then I got 95.
No,
No, I said before
Now,
I took the test.
if there's friction, and there is going to be friction, okay? There is going to be friction. You're going to use U equals force friction over force normal. But listen to me. It is only this mass that's going to determine this frictional force, okay? This mass has nothing to do with it. It's only the mass that's up here on the table, okay?
So what's Fn? Is that just Fg?
Well,
Since it's
on a
flat.
flat surface, it's just
Okay.
your normal force.
It's been so long since we've been talking about this.
Well, this is why we're
Was it on our homework?
So it's also Fg cosine theta, but on a flat surface, you don't have to worry about the cosine part of it. Now, if I did something like this, okay, which is just basically a version of this, so what's the only difference between this and this? Now there's going to be what?
An incline.
Yeah, now there's going to be a force parallel that's always going to act down the inclined plane.
And Fg is going to change.
Now,
Or no, Fn.
the other thing that's going to happen is they're going to have something like this with the Atwood machine. Let's say this is 0.2 kilograms, and let's say this is 0.1 kilograms. Okay? Which direction is it going to go?
Left.
Down.
This one's going to go
Down for sure.
This one's going to go up.
One's gonna go up and one's gonna go down.
One's going to go up. One's probably bank on that.
Well, up, no, if they're even though.
And again, you can go through and set up a chart and go, okay, net, FAP, FOP. Okay? Or if it's going to accelerate, what is your net force not going to equal?
Zero. No way.
So, what are you going to use as your applied force?
The bigger of the weight.
Yeah, so this is going to be 0.2 times G. This one's going to be,
0.1.
and the difference between these two is your,
Net.
and then to get your acceleration,
Wait a second. Can't you
Dude.
just take 0.1 G then?
Yeah, that's it.
So all you gotta do is take
He's just making it a lot harder
Equations.
and longer.
okay?
So
But
really
at the
you
end of the day, when you're going to get this acceleration, what are you going to divide by?
total.
You're going to divide by 0.3 kilograms, okay? Just not the 0.2, just not the 0.1, by the total mass.
Alright, so you're taking 0.2 times G minus 0.1 times G divided by 0.3.
Yes,
And then you got yourself the net.
yes. No, then you have your acceleration.
Then you have the acceleration.
Yes. Okay,
Alright,
now, let's start at the beginning.
I have a question on the purple sheet still. Is there going to be a magnetic force on the free body diagram?
Yes.
Yes.
Force opposite.
Okay.
We don't have to know like in depth what's happening.
With what, the magnetic force?
Yeah.
No, I'm actually, on the test, I will either give it to you and say, this is the magnetic force.
Otherwise known as FOP. right? Always.
Yes, because your magnetic force is always going to be in that opposite direction of motion. Or I'm going to give you all the other information and have you determine what the value is.
But what I'm saying is, there's no multiple choice questions where you're like, what's actually happening?
No.
All right. So is there going to be a question where we have to like add the magnetic force and force friction to get FOP?
That's a very real possibility.
So, but it'll.
But I have to give you the numbers.
All right.
Okay. Now let's start at the beginning. What are the 4 fundamental forces? What's one of them? Ellie. What's one of them? Force of gravity. As the distance increases between 2 objects, what happens to the gravitational force? As the distance between 2 objects increases, what happens to the gravitational force?
Decreases.
It decreases. The same thing is true of like this magnet. Okay? If the magnet's close, it's very, very strong. As the magnet gets further away, the force becomes weaker. And the same thing is true of gravitational fields. Okay. That's one of them. What's the broadest and most diverse of all of the 4 forces? Kendra.
Why do you always call on me for these ones?
Okay. Okay.
Is it force applied?
No. Okay. No. It's
Where
one of the
you-
4 fundamental forces. Force applied is not one of the 4 fundamental forces.
No. One of the 4 fundamental forces that is. What's the question?
Think of the free body.
Which
No, don't think
don't
of
think
it.
of it. Don't listen to Hunt. Okay, do not listen to Hunt.
Push, pull, lift, and heat. Then you got.
Dear Lord, we're not flying an airplane. Okay. I'll give you a hint.
Okay.
Okay? There's 4 fundamental forces. Gravity is one of them. The other 3 are the strong nuclear force, the weak nuclear force, and the electromagnetic force.
Those are so old. Really. Like.
That's why I said that started at the beginning.
Do we even need to
We
know
never
this?
covered that.
I spent an entire day
Do you not
going
remember the
over it.
balloons?
Honestly,
Making the can roll.
All right, guys. which
Eric
is
thought I
the
should be
strongest
burned
of
at
the
the
4?
stake because I was a witch.
Oh, is that like this?
You know,
Yes.
the only people that would
Yeah,
burn
your
it
hair
are
was-
witches.
Is it the static where my hair went all like?
Yes.
That's what.
Yes.
The strongest is the strong force. guys.
Yes, the strongest is the strong nuclear force because it holds the protons together because they naturally want to go flying apart. Now, here's the one force I will not ask you about is the weak nuclear because it's important, but it only is involved when you study nuclear reactions in depth. So the one that I will not ask you about is the weak nuclear. Okay? So the electromagnetic force is the most diverse. It creates friction. It creates electricity. It's why we have light. Okay? It's why we have magnetic fields. Okay? So it's what holds the graphite together in your pencil, but yet still allows you to write on a piece of paper. Okay? It's what holds your skin together. It's what keeps you from falling through the center of the earth. It creates friction. Okay? So,
Honestly, like.
It's what gives us our phones.
it's what gives you your phones.
Friction is crazy.
It is. Okay.
On some
Now, let's talk Newton's 3 laws. Newton's first law.
So when I like rub this on my skin,
I don't care.
do protons just like evaporate? Where do those
Let's
protons?
just don't even go. Okay. Newton's first law of motion. An object at rest remains at rest or
An object in motion stays.
stays in motion. Now, okay, now there's 2 parts to this motion. There's 2 parts to the motion because it's a vector quantity. If you either change the magnitude, making it speed up or slow down, or if you change the direction. Each of those is an acceleration. So if you see something that is not traveling at a straight line at a constant speed, there has to be a force acting on it. Speeding up, slowing down, something to make it turn. Okay? So that's Newton's first law. Second law is hanging on the sign in the middle of the room. F equals ma. Right? That's it.
If we miss
It's
that
the
one,
only mathematical one in there. Third law.
Number, every
For every force,
equal in opposite
there is
which
an equal and opposite
I still don't
force.
understand that. So when I hit the table, why doesn't my hand just go up? If there's an equal and opposite force.
If there was not a reaction force, your fist would go through the table.
Oh, that's true, it just stops it.
Yeah.
Alright.
Now, or if you push down on it, okay, so let's say you're
Holds
pushing
it up.
down on it, and then somebody yanks the table out from underneath you.
That's why, yeah.
Yeah. Okay.
Alright.
Good with that? Okay. So here's what you need. You need to know the 4 fundamental forces. Don't worry about the electromagnetic or the weak nuclear. You need to, and simple examples of those, and Newton's 3 laws. So those are the only things you really need to memorize. Now, keep in mind what you're going to have in terms of an equation sheet. You're not going to have like the equations for an Atwood machine. Here's the dichotomy of this test. It's a very, very broad topic test, but basically if you look at what your equations are, you have mu equals force friction over force normal. You have F equals ma, you have Fg sine theta, you get force parallel, and you have Fg cosine theta, you get force normal. Those are about the only equations that you have, okay? You just have to know how to use them, okay? You have to know how to use them. And when you get onto a problem, and on a lot of these problems, this is what I did when I worked, and you'll see this when you see the solution guide. On a lot of these problems, I went through and I set up a chart like this. So if you're not sure what to do, start with this chart. And literally, here's the whole key. Every problem that you have to work on this test is only one of 2 possibilities. You're either at a constant velocity, where your net force is 0, or you're accelerating. That's it. There is nothing else in town. So say, hey, constant velocity. I'm going to make everything add up to equal to 0. Hey, I'm accelerating. My net force is not going to be 0. Start with that. Okay, I'm done. I'm going to hand out, I'm going to give you a blank review, and then the review with the answer keys. So, you're on your own.
No.